Now we're going to look at an example using a Zener diode voltage regulator. So we want to design a regulator that's going to power a car radio at 9 volts, and we're going to do this from a car battery that can vary between 11 volts and 13.6 volts. We're told that the current in the radio can vary from 0, which corresponds to the radio being off, all the way up to 100 milliamps, which would be full volume. So what we're going to do is let's use the same circuit format, because of course that's what our equation was for that particular circuit. Again, we could rederive a similar equation if our topology changed a little bit, but to keep things simple, let's just go ahead and keep this format. And note that our VL, which is across our radio, is the same as our Zener diode voltage VZ, so sort of by design, right? Because our VZ is constant, we want our VL to be constant, we put the two in parallel. So what is it that we're trying to find then? So we already know this topology, we have all of these variables up here. So what do we want to know? So we don't know the value of this resistor Ri, and we don't know how much power our Zener diode needs to be able to handle. So we want to find Ri, and we need to know our diode specs, or our required specs for our diode. And we're going to do the same thing for our resistor too. We need to figure out how much power it needs to be able to dissipate. Okay, so let's start with that equation we had from our previous video, so that big long mess. So we're going to keep that assumption, of course, that our IZ min is a tenth of IZ max, so we can use that equation. So we had our IL max, which in this case is 100 milliamps. So if I use milliamps here, then my answer will just be in milliamps. We multiply that by the quantity of our VPS max, which in this case is a VB, so 13.6 minus our VZ. And as we set up here, VZ wasn't explicitly given, but VL was, and we know VL is equal to VZ, so we know that that is 9, minus, and then we had IL min times a bunch of stuff, but our IL min is 0, so that whole second term is just going to go to 0. In the denominator, we had our VPS min, in this case that's our VB min, which is 11 volts, minus 0.9 times our VZ, which we said is 9 volts, minus 0.1 times our VPS max, which is the 13.6 volts. So plugging all of that in, we get approximately 299 milliamps. And again, because I had this current up here in milliamps, my answer is going to be in milliamps as well. All right, so we could also calculate, if we wanted, our IZ min just by dividing that value by 10, and that comes out to be about 29.9 milliamps, of course. Okay, so now coming back to what we actually need to find, we need to find the value of that resistor Ri. So we can use either of the two equations from our previous video. So using the numbers I had written there, I'm going to use equation 4 from the previous video, or again, if you're following along in the Canvas notes, the previous page. So using that, okay, so previous video, so we have Ri is approximately equal to, so our VPS max, or our VB max, which is 13.6, minus our VZ, divided by our IL max, which is, our IZ max, which is 0.299 amps, plus our IL min, which is 0. So using stored values in the calculator, I get an exact value of 15.4 ohms. So that would be the required value for our input resistance R sub I. So now what we want to do is we need to figure out the diode specs. But let's just go ahead and do a general power analysis so we can figure out how much power our Ri should be able to handle as well. So we're going to look at the power analysis for our resistor and diode. Okay, so let's start with our resistor since we were just working with that. So Pri max, and again using equations from the previous video, or it's pretty easy to just redo that KVL in that left loop here. What we can see is that the power, if we use V squared over R, The voltage across that resistor is VPS, or in this case, VB. And if we're talking about maximum power, that's going to be maximum VB minus the Zener voltage, V squared divided by R. So we get something like this. So now we just plug in values for this problem. So we have 13.6 minus 9, quantity squared, divided by 15.4, and we get approximately 1.37 watts. And so that's a relatively large power compared to what the types of resistor we use in the lab. So remember, most of the resistors up in our lab are quarter watt, so 0.25 watt. So we would need to be careful to choose an appropriate resistor that could handle this much power. So let's also analyze the power for our Zener diode. So the maximum power for our Zener diode, P sub Z max, is just equal to the maximum current times our Zener voltage. So IZ max times VZ. And so this is going to be approximately equal to that 0.299 amps times the Zener voltage of 9 volts. And that gives us approximately 2.69 watts. And so again, as we've said before, you want to be careful not to over-design. So maybe we don't need a Zener diode that can handle 20 amps or 20 watts rather. But at the same time, we want to make sure that we have some type of safety margin in case it goes a little bit above that during normal operation. So hopefully this example has given you a little bit better idea of how to use that equation for our Zener diode regulator.